Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a foundational concept that's been bugging AI researchers for decades, the symbol grounding problem.
Yeah, it's one of those problems that just won't go away, right? Like we keep making progress, but this core issue of how symbols get their meaning, how they connect to the real world, it's still there, lurking.
Lurking is an understatement. I think it's a fundamental flaw in a lot of current AI approaches, especially those that rely heavily on just throwing data at the problem.
Absolutely. It's that bridge between the abstract and the concrete. Without it, are we really building intelligence, or just incredibly sophisticated pattern matching machines?
Exactly. So for our listeners who might not be intimately familiar, let's lay out the basics. The symbol grounding problem, as articulated back in 1990, asks, how do symbols in a system like a computer acquire meaning? How do they become connected to the real world in a way that isn't just circular?
Right. Because if all your symbols are defined in terms of other symbols, you're just stuck in a closed loop. There's no external anchor, no connection to sensory experience.
Think of it like trying to learn a new language just by reading a dictionary in that language. You're just going to go around in circles, defining words in terms of other words you don't understand.
And it gets even trickier when you consider that the real world isn't just some objective thing out there. It's filtered through our senses, processed by our brains, and ultimately represented in some internal format. So, the problem isn't just connecting symbols to objects, but connecting them to internal representations of those objects.
Mm-hmm. And that internal representation is where the neuroscience comes in, right? Because how does the brain do it? How does it take raw sensory input and transform it into something meaningful?
Well, that's the million-dollar question, isn't it? Deep learning has made huge strides in pattern recognition, but I think it's still an open question whether it can truly ground symbols in the way that a human brain does. I mean, look at image recognition. A neural network can identify a cat in a photo with incredible accuracy, but does it actually understand what a cat is?
That's my biggest concern. It recognizes patterns, sure, but it doesn't understand the essence of catness. It doesn't know that a cat is a living thing, that it meows, that it likes to chase mice, etc. It's just a statistical correlation.
Exactly. And that's where I think the spatiotemporal aspect comes in. A cat isn't just a static image. It's something that moves through space and time, interacts with its environment. We need algorithms that can capture that dynamic aspect, that can represent objects as something that exists in a four-dimensional world.
Yes, and I find myself thinking about how the brain handles different types of memory: episodic, semantic, procedural. Each seems to contribute to this grounding process. Episodic memory ties symbols to specific experiences. Semantic memory provides general knowledge, and procedural memory allows us to interact with the world.
You know, I've been thinking a lot about large language models recently. They're surprisingly good at generating text that seems meaningful, even though they're just trained on massive amounts of data. Maybe there's something emergent happening there, some form of grounding that we don't fully understand yet.
I'm still skeptical. They're good at mimicking human language, but they don't actually understand what they're saying. They can generate a coherent paragraph about philosophy, but they don't actually believe in anything. It's all just pattern recognition.
I think the key difference is that humans have an internal model of the world. We can imagine scenarios, simulate outcomes, and reason about counterfactuals. Language models, as far as we know, don't have that kind of internal representation.
Right. So how do we build that internal model? That's where I'm focusing my efforts, especially with MemOS. It's an attempt to create a memory system for AI that's not just about storing and retrieving data, but about building up a rich, interconnected representation of the world.
See, that's what I'm excited about. I think a more sophisticated memory architecture is crucial for moving beyond the limitations of current deep learning. If we can find a way to efficiently store and retrieve relevant information, we might be able to get away with using smaller, more interpret-able networks.
But it has to be more than just efficient storage. It has to be structured knowledge, right? Symbolic representations that can be manipulated and reasoned about. Otherwise, it's just a bigger, faster version of the same problem.
Exactly. And that structure needs to be spatiotemporal. The relationships between objects, events, and locations need to be explicitly represented, not just implicitly encoded in the weights of a neural network.
So let's talk specifics. How can we integrate these different ideas? Otto, you mentioned large language models. How do you see them potentially contributing to solving the symbol grounding problem?
Well, I think they're showing us that it's possible to learn complex relationships from raw data, even without explicit symbolic representations. The question is, how do we extract those relationships and make them more explicit? Maybe we can use language models to generate symbolic descriptions of the world, and then use those descriptions to train other AI systems.
That's interesting. So, use the language model as a kind of teacher to create a more structured knowledge base. But how do we ensure that the language model is actually grounding its symbols correctly? It's still just learning from text, which is itself a symbolic representation.
That's the key challenge. We need to tie the language model's output to sensory input, to real-world experiences. Maybe we can use it to generate descriptions of images or videos, and then train another AI system to map those descriptions to the corresponding sensory data.
That's where multimodal learning comes in, right? Combining information from different sensory modalities, vision, hearing, touch, to create a more complete and grounded representation of the world. There's a lot of research exploring the integration of language and vision, for instance.
Yeah, and I think that's a promising direction. If you can train a system to understand the relationship between words and images, it starts to build a richer understanding of the meaning of those words. It's not just memorizing definitions, it's actually seeing what those words refer to in the real world.
But even with multimodal learning, I still think we need explicit symbolic representations. We need to be able to reason about the relationships between objects and events, to make inferences, to plan actions. And I'm not convinced that deep learning alone can provide that.
I agree. We need a way to represent knowledge in a more structured and interpretable way. That's why I'm so interested in algorithms that can work with different coordinate systems. If we can represent objects and events in terms of their spatial and temporal relationships, we can start to reason about them in a more flexible and powerful way.
Can you give us an example of how that might work, Donald?
Sure. Imagine you're trying to teach an AI system about the concept of going to the store. A simple approach would be to just show it lots of videos of people going to the store, but that doesn't capture the underlying structure of the event. A more sophisticated approach would be to represent the event in terms of a sequence of actions: leaving the house, walking down the street, entering the store, selecting items, paying at the checkout, leaving the store, returning home. Each of these actions can be represented in terms of spatial and temporal relationships. The location of the person, the direction they're moving, the time it takes to complete each action.
So you're essentially building a kind of spatiotemporal map of the event. And then the AI system can use that map to reason about the event, to answer questions like, what happens after you enter the store? Or how long does it take to go to the store?
That makes sense. But how do you handle the variability in the real world? Not everyone takes the same route to the store. Not every store is laid out the same way. How do you create a representation that's both structured and flexible?
That's where the ability to translate between different coordinate systems comes in. You might represent the route to the store in terms of GPS coordinates, or in terms of landmarks, turn left at the gas station, or in terms of a topological map, take the second exit. The AI system needs to be able to translate between these different representations to adapt to different environments.
And that's where MemOS comes in, right? By creating a memory system that can store and retrieve information in different formats, we can potentially bridge the gap between the raw sensory data and the abstract symbolic representations.
So you're envisioning MemOS as a kind of central hub where all these different representations can be integrated and accessed. It's not just a storage device, it's a reasoning engine.
But it needs to be more than just a database. It needs to be able to actively manipulate and transform those representations, to perform logical inferences, to generate new knowledge.
And it needs to be able to do all of that in real time, to interact with the world in a dynamic and responsive way. The spatiotemporal relationships are constantly changing, so the memory system needs to be able to keep up.
Exactly. The brain is incredibly good at that. It's constantly updating its internal model of the world based on new sensory information, and it does it in a way that's both efficient and robust.
So how do we build an AI system that can do the same thing? What are the key architectural principles that we need to follow?
I think we need to move away from the purely data-driven approach of deep learning. We need to incorporate more explicit symbolic reasoning capabilities into our AI systems.
And we need to focus on representing knowledge in a way that's grounded in the physical world. That means paying attention to the spatial and temporal relationships between objects and events.
Yes, and I believe understanding the neuroscientific underpinnings of memory and cognition is crucial. We need to look at how the brain actually solves these problems and try to emulate those solutions in our AI systems.
So where do we go from here? What are the most promising research directions for addressing the symbol grounding problem?
From my perspective, I think we need to focus on building more biologically inspired memory systems. I want to explore how we can model the dynamic interplay between neural circuits and symbolic processing, how we can create AI systems that learn and remember in a more nuanced way.
I'm still optimistic about deep learning. I think we can find ways to incorporate more structured knowledge into deep learning models to bridge the gap between symbolic and sub-symbolic representations. I want to explore how we can use large language models to generate symbolic descriptions of the world, and then use those descriptions to train other AI systems.
I'm convinced that we need to develop more powerful neuro-symbolic algorithms. I want to explore how we can combine the strengths of neural networks and symbolic reasoning to create AI systems that can both learn from data and reason about the world.
I think the key is to develop a core algorithm that can intelligently leverage different coordinate systems. I want to research how we can build in the ability to effectively translate between spatial, temporal, and abstract representations, and how this relates to the grounding of symbols.
So lots of exciting avenues to explore. The symbol grounding problem remains a challenge, but by combining insights from neuroscience, AI, and cognitive science, I think we can make significant progress in the years to come.
Definitely. It's a complex problem, but it's also a fascinating one. And I think the potential payoff, building truly intelligent machines, is well worth the effort.
I agree. It's not just about building better AI systems, it's about understanding the nature of intelligence itself.
Absolutely. And by tackling the symbol grounding problem, we're forced to confront some of the most fundamental questions about meaning, representation, and consciousness.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion stimulating, and we encourage you to continue exploring these ideas on your own. Until next time.